today what I'm going to talk about is the minimum spanning tree problem. Tree problem. Oh, and I should mention, when I gave my lecture on Wednesday, I said that there's another scheduling type problem that we would look at. And then because I had a substitute on Friday, it seemed, and that was going to take much less than an hour, it seemed better just to move on to the next topic, which is Dijkstra. But I will come back to that scheduling type problem maybe today or maybe Wednesday as we move into another topic that it's related to. But anyway, so today I want to do what's the next topic just after Dijkstra in the text, because they're very related in some way. Minimum spanning tree problem. And let me just show you graphically an example of that problem. So you have a graph, and it's undirected. There are no directions on the edges. And every edge has a weight or a distance or a cost. You can think of whatever you like. Anyway, there's some number that's associated with each edge. And I'm just making these up. And hopefully this will be somewhat more interesting. And so you can think of this as a system of potential roads, let's say, so try to give some interpretation of this problem. These are cities, the nodes are cities, and the edges that are drawn here are potential roads that might be built. We haven't built anything yet. And if you build this road, it costs you 1 something or other. If you build this road, it costs you 5. This road costs 7, etc. And the goal is to build a system of roads so that you can get from any one place to any other place, with the minimum total cost. So if we consider these, the node, let's say, is a city, and an edge is a potential road. It could be built or purchased or rented or whatever interpretation you want to think of it. And the goal is find a cheapest set of edges to connect all the cities, or cheapest set of roads to connect all the cities. And lots of other little interpretations you can come up with for this kind of a problem. You could think of each node, again, as some destination. The edges here, let's say, are now not roads, but fiber links that you could install to communicate from here to here. And again, this is each weight given there is a cost, and so on. There's lots of little interpretations. But generally, you have a graph with nodes and edges. You have weights on, non-negative weights on each of the edges. And you want to find a subset of edges of minimum total cost to connect together all of the nodes. Okay? Now, first observation, do we know how many edges we should take into this? Well, let me back up a minute and say, let S be an optimal, that means minimum cost, solution. Okay, then my question is, what can you say about the form of S? And let me remind you that these edge weights here are non-negative, or let's make it simpler, positive. Okay, so if we want to connect everything together and we want to minimize the total cost that's used, what can we say about the form of the set of edges that form an optimal solution? Yeah.
Well, since each edge connects two nodes, you can't have too many fewer edges than you have nodes.
Okay, so you're saying
You can only have, if you have n nodes, you can't have any less than n minus 1 edges.
okay, n nodes. There must be at least n minus 1 edges, because you all remember from some previous class that introduced a little bit of graph theory that if you have a graph that has n nodes and it's connected, there have to be at least n minus 1 edges. That's what's being referred to. So at least n minus 1 edges. What else might you say? Sort of on the flip side of that contribution. If there are n nodes, there must be at least n minus 1 edges. But what about there will be at most n minus 1 edges? Well, that's also true, and maybe uses a fact that's a little bit more subtle or you don't know. But so before we get to that exactly, let's just look back at this. What is the form of S? And what do I mean by form? Well, you'll know what I mean if you know what the answer of this question is. Is what? Okay, that's, yeah. Anybody else? The advantage of having you in the front is nobody else can hear you, so I get to ask the question twice. Okay, let's just do an example here first. Let's just look at this and see what do we think is the minimum cost set of edges that connects everybody. Well, it looks like 1 should probably be in there. And this 2, that would be a good choice. This 2 is good. Maybe to get over to here, we use this 4, and we still haven't gotten over from here to there. There's a 4. Okay. Does that connect everything together? Yeah, it does. Is that the cheapest total way to do it? Looks to me like it is, and we'll see more systematically in a minute. And what's the form of this? If the hashed edges are the ones that are in S in the optimal solution, what is the form of that solution? It's a tree. Okay? The set of hashed edges forms a tree, and in fact it connects all the nodes together. Well, that was a requirement, so that's what's called a spanning tree, and that's why this problem is called the minimum spanning tree problem. That is, if you came in and said, oh, the optimal solution to this, the set of edges S that has minimum total cost and connects everything together, looked like this, like it has a cycle in it. Well, that can't be right, that's the optimal or the minimum cost, because of this cycle, you could take out any one of these edges and still be connected. And because the weights are positive, when you took out one of these edges, the cost would decrease. So since the weights are positive, there won't be any cycles in the optimal solution, and a subgraph, a set of edges that doesn't have cycles, is either a tree or a set of trees, which are called a forest. But since the set of edges has to connect everything together, it'll just be a single tree. Okay, so the answer to this, what is the form of S? The answer, it is a spanning tree in the graph. Okay, and then it's a classic, very elementary theorem that you can prove easily by induction, that any tree on n nodes has n minus 1 edges. Okay, so the spanning tree, if the graph has n nodes, it'll have exactly n minus 1 edges, and that actually implies both of these, that it'll have at least n minus 1 edges, and it'll have at most n minus 1 edges, because in fact it has exactly n minus 1 edges. Okay? N minus 1 edges. Okay, so that's our problem. Find the minimum cost spanning tree, or minimum spanning tree, given a graph with positive weights. And now we want to find an algorithm or several algorithms, analyze the running time and prove that they're correct, and all the usual things. Okay, so we're in fact going to look at two algorithms. One is called Prim's algorithm. And one's called Kruskal's algorithm. I think the book actually does them in this order: Kruskal first and Prim second, but I think Prim is a more natural algorithm. And both of these algorithms are going to be proven correct. In fact, there's a third algorithm that's also discussed in the book that are going to be proven correct by the following lemma. So before I tell you what the algorithms are, let me look at this lemma. And here we're going to assume that the edge weights are distinct. So no ties. Okay? And later we can look at removing this assumption and seeing how you can address the case when there are ties in the edge weights. Assuming the edge weights are distinct, well, okay, if E, this is an edge, it goes from U to V, looks like this, U to V. Okay, I realized at this moment that using this capital S was at least a bad notation in terms of the book, because the book likes to use capital S in this discussion for something else. So let me just change this capital S somewhere, everywhere where I see it, to Z, in the form of Z. Do I have it anywhere else? Okay. So if E is the minimum weight edge between some subset of nodes S and the remainder of the edges of the nodes, V minus S. Okay, and then I'll put that up here. Then E must be in every minimum spanning tree of the graph. Okay? So we'll prove this lemma, but let me just give you some pictures. So what I'm saying is, here's the graph, call it G, and here's some subset of the nodes, okay? And here are the remainder of the nodes, V minus S. So V is the entire set of nodes. V is the entire set of nodes. Okay? And this edge E goes from a node labeled U to a node labeled V, where that crosses from the set S to the set V minus S. And we're saying that if E is the minimum weight edge between some subset of nodes S and the remainder of the nodes, V minus S, then E must be in every minimum spanning tree. So if this is, let's say, a 3, and all the other edges that cross from S to V minus S have weights that are larger than 3, 4, 14, 26, whatever, then this edge will necessarily be in every minimum spanning tree of the graph. So we can take a look at this over here, okay? Now in this little example, I did have some duplicate costs, so let's let this be 4.5, and this be 2.5. Okay. Now all the costs are different, and this still looks like the minimum spanning tree. Okay, let's just take a look at this subset of nodes. We'll call that S, and the remainder of the nodes, the complement of the nodes, V minus S, okay? And we have two edges that cross there, cross that partition. One has weight 2 and one has weight 7. Okay, which one of those is in the minimum spanning tree that we looked at? It's the one of weight 2. That's the minimum cost edge that crosses between S and V minus S. Okay, and you can let me try to clean this up a little bit so I can give you a more complicated, more complex example. Let me label these nodes. This is A, B, C, D, E, F. Now, this lemma, actually I think this has a numbering in the book, 4.16. One of the most irritating things about this book, by the way, in case the authors are listening out there or ever review these videos, they number their results, their statements of consequence, but they never say it's a lemma or a theorem or a corollary or anything. They just give it a number, and it's just really hard to refer to it. I refer to 4.16, but what is 4.16? To me, that was a lemma, so I'll call it. Okay. Yeah, my point was that this S is any subset of nodes. It doesn't have to be sort of a contiguous, nicely well-formed subset the way I first drew this as a circle and then the other circle. So any subset of nodes S should have this property. This lemma relates and applies to any subset of nodes. So now I want somebody to randomly pick a subset of nodes from A to F, but try not to make it all cluster together. Okay? So just shout out your favorite letter between A and F.
B.
B. Okay. What else?
E.
E. And somebody else say stop. Tell me when S finishes. Okay, next letter.
C.
C. Okay, somebody better say stop pretty soon. What?
Stop.
Oh, good. All right, so this is my S. This will now be S. And V minus S, well, we had A, B, C, so we have D, E, F. That's everything, right? Okay, so now we have, in this one we have A and C, A, C, and B, and E, It got clustered. Oh, well. And then we have D and F, okay, which are these ones over here. Okay, so we have a partition into S and V minus S, and the edges that cross from this set to that set, what are they? They're the one that's labeled 7, it's weight 7. It's the one that's 6, and the one that's 4.5. Okay? And the minimum weight edge that crosses between these two sets is weight 4.5, and that's the one that's in this minimum spanning tree. Okay? So we've proven this lemma by example, and proof by example. Okay, and that's not enough. We want to prove this, actually prove this correctly and completely. Okay, so here's the way this proof goes. This is a classic style of proof in minimum spanning trees, and in fact in a larger class of problems in mathematics called matroid theory, matroid theory which generalizes linear algebra, and you might see this kind of style of proof in linear algebra. At any rate, so let's let T be a minimum spanning tree of G. G is the graph, where the lemma is violated. Okay? So essentially we're saying assume that the lemma is false, and here's an example that shows that it's false. So T is just some minimum spanning tree of G where the lemma is violated. Okay. Well, what does that mean? It's violated. That means there is an edge E equals UV, where U is contained in a subset S, and V is contained in V minus S, and E is the minimum weight edge across S to V minus S, but E is not in T. Okay, so this is just setting up what it means to be a contradiction. T is a minimum spanning tree. Where the lemma is violated, that means there has to be some edge E that connects U to V, where U is in some subset of nodes, and V is in the complement subset, and E is the minimum weight edge that crosses from S to V minus S, but E is not in T. Okay, everybody see that this is just setting up the contradiction, setting up what it means that the lemma is not true. So we can draw a picture. So here's S, and here's V minus S, and here's E. Okay, and all right, here's E. Okay, now the minimum spanning tree, and E is not in T. So E is assumed not to be in this minimum spanning tree that we say exists. Okay. But T is a minimum spanning tree. It's a spanning tree. Okay? So there has to be some way in the spanning tree, in T, that U can get to V, because that's the requirement of a spanning tree. It connects, the subset of edges connects every node to every other node. I mean, connects not directly through a single edge, but through some path. Okay, so in T, there is a way of getting from U to V, not by edge E, because edge E isn't in there. Okay, there must be a path in T from U to V, because again, that's the requirement of a spanning tree. It connects together all of the nodes, and from any node you can get to every other node. So from U, there's some path over to V that is in T. This path is in T. Okay? Well, it starts in U. This path starts in U and ends in V. So there has to be an edge that goes from S to V minus S. There has to be an edge in this path that gets you from S to V minus S. So you can think of, if you go along this path, there's some last node in that path that's in S. Okay? And so where's the next node? If it's not in S, it's in V minus S, because S and V minus S together make everything. So there has to be some edge in that path that goes from a node in S to a node in V minus S. There's an edge E prime in the path from where E prime goes from S to V minus S. Okay? Oh, I didn't name this. This is E prime. So we have that picture. Okay? Now, what do we know about the weight of E compared to E prime? Yeah, because these are two edges that cross from a subset S to a subset V minus S. Okay? So here we have this partition S to V minus S, and E was assumed to be the minimum weight edge that crosses from S to V minus S. So the weight or cost of E is strictly less than the weight of E prime. And it's strictly less because all the edges have distinct weights. Yeah?
How do we get the weight of E is strictly less than the weight of E prime?
Well, we started over here by saying that the lemma is not true. So assume the lemma is not true, that means that there's a tree T, which is a minimum spanning tree, that violates the lemma, where the lemma is violated. That means that there is some edge E, which is in some subset S, where U is in subset S, and V, the other end of E, is in subset V minus S, and E is the minimum weight edge across that partition from S to V minus S. So it's in the premise of it's the beginning of the proof. Okay? So now I'm just using it. I'm using the fact that E is the minimum weight edge that crosses from S to V minus S. So it must be strictly less than the weight of E prime. And it's less than or equal because it's the minimum, but all the edges have distinct weights, so it's strictly less. Okay? So now, I guess I don't really need the example anymore. Okay, so now consider replacing E prime with E. Okay, so you take all the original tree T, but you now take E prime out and you add E in. Question, is this now a spanning tree? Is it still connected? Okay. Well, everything that was connected inside here is still, that's unchanged. Everything that's connected inside here is still connected. If ever you want to go from S to V minus S, previously you had to go along E prime, but now you can get from here over to here, because this is still connected, and get across going this way. Or just another way of thinking of it this way is, since this is a cycle, when you have both of them in there, since this is a cycle, and we know we can get from here to here, okay? So anytime you were going to go from here, from some node in here, to some node over there, by going through this edge, if you're ever going to do that. Now, if we don't have that edge, what you would do instead, you could certainly go up to that node, come down to this node, cross over, and then go up to that node, and then cross that way. So certainly you can still get from everything, from every node to every other node. Because again, any path that would have used E prime to connect two nodes along a path can now use this portion of this path we've been considering, use E, and then use that portion of that path. Okay? So it's still connected. Now consider replacing E prime with E. The graph is still connected. So T minus E prime plus E is a spanning tree. So this is another spanning tree of G. But what's its total cost in comparison to T? It's less, because this cost was strictly less than this cost. Its cost is strictly less than T, but that's a contradiction. Contradicting the assumption that T is a minimum spanning tree. Okay, and so that's the proof of the lemma. So we started out, we had the statement of the lemma, we started out with assuming that was not true, and assuming that T was a minimum spanning tree, and we've run to a contradiction. The contradiction is that T can't be a minimum spanning tree, because here's another spanning tree that's actually cheaper. So that's a contradiction, which means that when we assumed here that the lemma was false, that won't work, and therefore the lemma is true. Okay, so we've proven this lemma, and this is the essential mathematical insight that's going to allow us to see different algorithms are correct. Different algorithms. I used to say in some classes that once you understand this, or even before you understand this, it's almost impossible to come up with an algorithm for the minimum spanning tree problem that's not correct. There are some that are not efficient, and there are some that are more efficient than others, but people can think of all kinds of algorithms that are quite different, but somehow the problem has enough intuitive appeal and structure that people come up with correct algorithms. I know about 5 or 6 different ones. However, having said that for many, many years in many different classes, actually occasionally people do come up with algorithms that aren't correct. But most algorithms you're going to think of will at least be correct. So who would, now with that form of intimidation, who's brave enough to actually suggest an algorithm where you don't know it already, if you haven't seen this problem previously? Who would like to suggest an algorithm for finding a minimum spanning tree? Yeah.
Well, we could just start with one node and then take the smallest or the minimum weight edge to anything the rest of the Okay, and make that our S, and then take the minimum weight edge to our V minus S, which would be everything else.
Right. That's using this lemma repeatedly. So the algorithm that's being proposed, well, my board work today is terrible because I'm going all over the place. So this is still part of the proof. This is still part of the proof. I'd like to leave up the proof as long as possible. This is the statement. Well, there's no way of doing that. Okay, so this is the statement of the lemma, which we want to leave up there. And we'll have to cannibalize the proof in a minute, but right now I'll use this portion of the board. Okay, so here's a proposed algorithm. You're just going to pick some node V to be in the minimum spanning tree we're going to build. Well, every node eventually is going to be in the minimum spanning tree, so that's certainly an okay thing to do. And then the main thing is find a node. Let me make this U instead of V. Find a node V. Oh, sorry. Pick some node in U to be in T. Actually, let me just to be in S. Okay. Then find a node V that's not an S, okay, which such that the weight of edge E equals UV is the minimum weight edge across S to V minus S. Okay? So you find that node, and then you put V into S and E into T. So you're building a minimum spanning tree T, and you put the edge E, which means also putting its endpoints, into T. Okay? And now we're going to iterate. So is everybody clear on what's being proposed here? So we're going to be growing this set S. It starts out with just a single node, and then we're going to find a node V that's not an S. Such that the weight the edge UV, well, I better emphasize that U is an S. U is contained in S, is the minimum weight edge across that partition S to V minus S. And then we're going to put V into S, little v, not capital V, into S, and E into the tree T. And we'll keep doing that until when? Well, until all the nodes are in S. Okay, so we're going to repeat until, or maybe it's better to say while. In fact, I could do this like that. While S is strictly contained in capital V. Okay, we haven't included everybody yet. Do that and that. Okay, so this, I don't need that in there anymore. Okay, let me do a little example. We erased, unfortunately, the previous example, but let's just make up another one. 1, 4, 5, 2, 3, 7, 6, 2. Hopefully it'll be something interesting. Okay, so we could start here, for example, and this one Yeah, so that'll be an S initially. And if that's my initial S, everything else is V minus S. So this is the cheapest edge, minimum weight edge that crosses from S to V minus S. So we'll put that in. And now these two nodes are in S. And the candidate edges that go from S to V minus S is this one, and this one. Well, the minimum weight edge that crosses there is this. The candidate edges, the new S is these three nodes, and the candidate edges, now this is no longer a candidate because it doesn't cross from S to V minus S. But the candidate edges are this one that's 5 and this one that's 7. The cheapest one is 5. And so now S consists of these 4 nodes. The edges that cross from S to V minus S is the 7, the 4, the 2, and that's that. 2 is the cheapest, and now the candidate edges that cross are 7, 4, and 3, and the cheapest is 3. Okay, so the minimum spanning tree in this case is just a little path, but we followed the algorithm. Yeah? Oh, okay, I had ties. Okay, 2.5. Right. And notice, because we started here, this 2.5 is actually bigger than this 2. So we're not taking these edges in order of their weight. Well, we had 1, 2.55, and this is 2, so that's smaller than that, and a 3. So it's not in some strict order of the weighting. It's following this algorithm, which has a certain topological property of expanding outward. Okay? So this algorithm that was proposed is actually called Prim's algorithm. Very convenient that the proposal was exactly the algorithm I was going to show you first. So that's called Prim's algorithm. And why is it right? Why is this algorithm correct? I claim this finds a minimum spanning tree. Yeah?
Because it just uses the lemma, reduces it multiple times?
Yeah, this is really directly using the lemma. Every time it chooses a new edge, it is explicitly seeing a subset S, which is the set of nodes that have been taken already into the tree, and a subset V minus S, which are the nodes that are not yet taken into the tree. And we are explicitly choosing the minimum weight edge that crosses from S to V minus S. So since the lemma says that such an edge must be in every minimum spanning tree, and I didn't emphasize that when we were doing the proof, that it's in every minimum spanning tree. Why? Because we started in the proof, we started with an arbitrary minimum spanning tree T and ran to a contradiction. That tree T did not have edge E in it, and we ran to the contradiction that T couldn't be a minimum spanning tree. So, in fact, every minimum spanning tree has to have that edge E that's described in this lemma. So during the algorithm, when you take an edge that is the minimum weight edge between S, the nodes you've selected so far, and V minus S, the nodes you haven't taken so far, when you take that minimum weight edge, that has to be in the minimum spanning tree for this graph, because it has to be in every minimum spanning tree for this graph. So you're not making any bad choices as you move myopically or greedily through the algorithm. Okay? So that's the correctness proof. And there was that fine issue about every. If this lemma did not say that it was in every minimum spanning tree, if it just said it was in some minimum spanning tree, then it wouldn't be so immediate to prove that this was correct. That sounds like a really good homework question. You know, suppose this lemma only showed that edge E was in some minimum spanning tree. Why wouldn't the proof that this algorithm is correct hold in that case? Yeah?
Can actually be minimum spanning trees, there are distinct weight edges.
Wait, can you say that again louder?
Okay, if all the edges have distinct weights, can there actually be multiple minimum spanning trees?
Oh, okay. Well, that sounds like another good homework question. If all the edges have distinct weights, can there be multiple minimum spanning trees? Okay, can there be more than one, or is the minimum spanning tree unique? Okay, we have this lemma, and if you think about this lemma, it gives you the answer. So was that your question? Yeah, okay. So I'm not going to give you the answer, but you can get the answer by thinking about, by applying this lemma. And I'll put it on the homework. Or the midterm, or somewhere. Anyway. It might actually be in the book. It's a classic issue. Okay, so this algorithm is correct. What about its running time? Okay, the running time, I think on Friday you saw a time analysis for Dijkstra where you used a min heap in the implementation. Okay, so if you use a min heap in this algorithm, min heap, Prim's algorithm can be implemented in big O of m log n time, where m is equal to the number of edges in G, and n equals the number of nodes. Okay, well, I haven't shown you why the min heap is in there, or discussed really the implementation. I'm going to let you look at the book. It's a half a page or so for this discussion, because I want to get on to Kruskal's algorithm. We only have 3 minutes or 4 minutes left. Okay, so Kruskal is a different algorithm. Kruskal is the following kind of algorithm. Here we're going to sort the edge weights, or edges, by weight, min first. So smallest weight edges first, we'll sort them smallest to largest weights. And then we're going to, while S is strictly contained in V, we haven't put all the nodes in there yet, choose the smallest weight edge, not in T, that hasn't been selected yet, and not forming a cycle with the edges already in T. So we have the edges sorted by weight, and we're just going to look at the smallest one first and throw it in, because that isn't going to cause a cycle. And then take a look at the next edge that's in the list, and the next edge and the next edge, and always ask, well, make sure it's not in the tree already, which it won't be because we're looking at the edges in order, never repeating looking at edge. But make sure it doesn't form a cycle with the edges that are already taken. And then place E UV into the tree and U V into S. So I've really run out of time, and you can prove the correctness of this algorithm also by using this lemma. It's a little more complicated proof than the proof of Prim's algorithm, so I'll do that next time. And but you can read it in the book and think about it a little bit. But again, this correctness comes from this lemma, and also the implementation time is the same as before.